today's lecture is on something called spatial convolution. That is the convolution that you have learned for one sequence, but now extended to 2 dimensions. And we will not see it in this lecture, but in the next one, that this spatial convolution can also be done in the Fourier space, as you already know from one sequence. So the idea is that an image. Yeah, actually, this is interesting. So let us see. So let's say that we have an image. Here we have and we have seen a family of transformations that transforms this into a new image. And area of R is a function of, so that means a single point here is transformed into a single point there, so 1 to 1. And now we will extend this to a new family where the whole region is transformed into a point. And then if you want to compute this one, the region will be color. So if we want to compute this one, the region is simply shifted. So the region is simply shifted. So this region is the one that computes this one. So there is a kind of sliding window, and we can represent that this way. So we can say J R is a function, but now a function of the neighborhood of I5. So it is not a point to a point, but a region to a point. So I think this is what is somehow implied here. So there is a transformation that takes a pixel RC in a neighborhood, but here the neighborhood has minus S plus S in rows plus B minus B columns. So you take all that neighborhood, you go through a function, and then that function results in it. So these are called local transformations or spatial filtering. So you want to call it. And so there is a moving window transformation. So there is a moving window. So this window, you transform the whole window into a point. And then you move the window. And one of those moving window transformations is convolution. So we will see. So say that we want to operate on that image, and that your operation will be the average of x squared. So the average of the nearby region. So you have this is the input, this will be the output, and then your operation is computing the average. And then if you want to compute the average somewhere else, so you move the window and then you move the average there. So for every neighborhood, you compute an average, and that is the output of that point. And if you want to move it to somewhere else, you compute the new average, you move the window, and you compute the average. So instead of 1 to 1, you go from a group to 1. And these are these moving window transformations. So if it is a linear transformation, you have some results here. So you have a 9 times 9 region that is moving. And for every region, you complete the average, that is what you put there. So this would be the result. And one of those is the convolution. So let's see the convolution. So the convolution is a special case of moving window where this function is linear. So if the function is linear, the function is linear and time invariant, this is this LTI transformations that you have from one unit. Then you can express it as a convolution. So it will be I composed with a kernel. And we have to define convolution. Okay, so let's define convolutions in one dimension. So let's define convolutions in one dimension. So let's say that you have an input signal x, x, n. You go through the kernel, and you produce an output. So on the output is x of n composed with h. So this is the sum from that only by the infinity of x, x of k, h, n minus k. And this is a following. So this is all this is a reminder of how it works in one dimension. So let's say that part here signal is like this. So this is your signal. Then you have your kernel. Let's say that your kernel is like this. I will not make it symmetric. Have an easy track how it's behaving. And then you have to compute that thing. Okay, so fix a given n. So look for one particular n. This n. Okay, so I have to construct x of k. So it's x of k. So x of k is the same as this x of n, only that I have to change the name k. By equal to k. So this one, this one, this one, and let's put the numbers. So let's say that this is 1. Okay, so we have now x of k. This goes there. Okay, that is good. Then we need h of n minus k. So we need here. So we need this is also the k axis. This is also this is k. This will be h of n minus k. So the minus k, so this minus here, this minus here makes that the kernel is free. So, and the n minus makes that the kernel is shifted to n. So it will be shifted to n. And then it is shifted to minus 1. And then you have all the zeros. Okay, so this is h of n minus k. So this point goes to here, and then it is flipped. And then you have to multiply it. So you have to multiply point by point. So this sum here have to sum all these values. Have to sum all of these values, and that will give you and that will give you the number 10. And then for the next n, you have to shift your kernel somewhere else. Okay, so like this, you can compute this convolution here. And you know that it is the same moving h or moving x. So in English, we can also multiply this with the sum from minus infinity to infinity of x of n minus h. Like it's the same. And this is another way of saying that the convolution is cumulative. So I can also compute this. Okay, so that is for one discipline. So how do we define the convolution for two disciplines? Actually, this can be extended to any number of dimensions. So in any number of dimensions, we have this. We have the sum as in one dimension overall space. So for all, I will make it in two dimensions, so that can be whatever. So now your k will be a vector, it will not be just a number, so it will be a vector. Or I, okay, this is well defined because I is an image and k is a location, so it's well defined. Times h n minus k. So it's the same that we had before, but now with vectors. And this I have expressed it in two dimensions, but it can be done in 3, 4, 5 dimensions. It is the same convolution formula that we had before, but now in any number of dimensions. And all you have to do is to consider vectors. Okay, so this is convolution. And this change of sign will also imply a mirroring. So when you look at in one dimension, there's a mirroring because of the minus sign. There's a mirroring of h with respect to the origin. So first you mirror and then you shift. Okay, so there is a mirroring with respect to the origin, and then you shift. And the same will happen in multiple dimensions. So first you mirror in 2 dimensions, and then you shift the location. So we will see all that in the slides. Here we have it. So the expressions are the same. I have expressed it as a function for discrete signals. We can write the convolution for continuous signals. So the equivalent of these in multiple dimensions. And for continuous images would be something like this. I we are continuous now. So I of is x of more with a kernel. And this is the double integral of space of x, I will call it k, as in the discrete convolution. Use k times h of r minus k difference of k. So everything now is a vector. this. So here we have I of R. So he has expanded the vectors. You have R minus K, H of K, differential of K. And here it is the same. So your image, there is a mistake here. This should be I. So I of R minus K, H of K, and then you sum over K. So it is the same. So convolution is a particular case of moving window transforms. Okay, then we have said there is a mirroring. So there is a mirroring means that if originally your image, your kernel looks like this, so this is the origin. So this would be the location 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and so on. And you mirror with respect to that. So the mirroring would be H00 stays in that same location, but H11 goes to the mirror position with respect to the origin. So it goes to here. And -1 goes to the position of 1, 1. And the same for all the others. Actually, this is the same. Mirroring in 2 dimensions is the same as a rotation of 180 degrees. Right? It only happens in 2 dimensions. In all other dimensions, it is a mirror. Okay, so then, so you have a kernel. This kernel will be the values with which you have to multiply. So this is the equivalent of these values here. This is the equivalent of these values. So I have names here. That is what it has done. So this is number A, this is number B, number B, and so on. So for a 2-dimensional kernel, we also have values. It has A, B, C, whatever. And then you simply multiply the values that you have underneath by the kernel values and sum all of them. This is exactly the same as we were doing in 1 dimension. So you have the image stays fixed, then the kernel is moving. You multiply the underlying signal by your kernel values, multiply, and then sum all those results. So it is exactly the same, but now in 2 dimensions. So take the fixed image, you multiply by the kernel values, you have to take care of the mirroring. And then you sum all of them, and that is the value for the output. Okay, so let's say that this is our original. Our kernel is a 3 times 3 array. So take these pixels, multiply by the kernel, and the kernel here is this one. So it is a 3 times 3 array. Okay, so that has to be here. Kernel upload. Now we need 2 dimensions. Y, X. Here will be the kernel. Kernel of kernel of R. Here we have number of. So it is 3 times 3, but I don't want to flatter it too much. And then these values are 1 9. So if you look from the top, you can also represent this H of I is also very often represented like this. 1 over 9, 1, 1, 1. You have to specify where the origin is. So the origin is there. Okay, so this is where the point is where the is looking from the top, and then we have a ninth everywhere. So this is just the average of 9 pixels. Okay, so this is what we are doing. So we multiply all these pixels, every one by 1/9, just add all of them, and the addition is put there. Okay. Okay, so now you know a property of convolution. You know that one of the properties of convolution is that so if I convolve delta R times the kernel, I should get a kernel. If the delta is shifted, I should get a shifted kernel. So let's see if this still holds for images. Okay, good. So let's say that we have a delta, we have a kernel. So the result should be the kernel. So what we will do is invert the kernel and moving to everywhere in the image. And I'm showing here only the ones, the positions where the multiplication is different from 0. So here we have ones in the black area, zeros in the white one. When you superpose, let's say that you move it to this corner, in this corner, the superposition will be 0 because this is 0 everywhere except here, that is 1. So it will be 0, and there is no color adding zeros. So let's keep the positions where the multiplication is different from 0. So this is one of them. So when you move your origin to this space, there is an intersection between the inverted and the delta. You multiply everything. So when you multiply, everything is 0 except this point. This point is 1. And then it is a lot of zeros times plus 1. And then you substitute that one in this location. This is the blue location here. Okay, so now we have 1 pixel. Let's move to the next pixel. So this is another location where it is different from 0. And then again, the sum is 1. Now we fill this pixel. And this one was the old one. Okay, and then this is another location where it is different from 0. It is 1. And you keep track of all of them. And this is the final result. That is the one that should be. So delta convolved with the kernel. The origin of the kernel should move to the delta location. So the origin of the kernel should move to the delta location. And then we have the standard error. Okay, so if your kernel is symmetric, then inverting or mirroring it doesn't affect the kernel. The kernel stays the same. So we will see 3 different ways of computing this convolution. One will be a moving window, as we have shown. Another one will be shift, multiply, and add, that we will see later. And the Fourier transform that will be the next lecture tomorrow. So let's say that we have one image. Okay, so let's see. So the moving window transform we have already shown. Okay, so keep moving your kernel and multiply and add. Okay, then this shift, multiply, and add. Okay, so let's see. Let's say that Let's do it in 1 minute. So let's do it in 1 minute. Let's look at this example here. So I can rewrite this kernel as A delta A plus B, sorry, plus B. Plus B delta N minus 1. I can write it that way. So when I complete the convolution, so I want to convolve x of n, convolve with an h. And this is x of n convolve with a delta n plus b delta n1. But because the convolution is a linear operator, then this is a minus x of n convolve with delta plus b x of n convolve with delta n1. And then this is a, and then x convolved with delta is just x. And x convolved with delta n minus 1 is x minus 1. So now you see the name of the tree. So what you have to do is shift and multiply. And then other signals that are also being shifted and multiplied. So you shift the whole signal, multiply by a factor, and then add to all other signals. So this is this second strategy. So this second strategy. So let's say that I have to convolve this image with a single delta. So simply I shift it to the location of the delta. So my image is shifted down by 16 pixels against all the dimensions. Then let's say that I have two deltas. So now it is I shift it to the 16 place, multiply by 1/2, and multiply the image by 1/2 because of the delta 0, and then add the 2. So this is what we will get. So we have this fixed image that is multiplied by a delta, the shifted one that is also multiplied by 1/2, and then add the 2.
Queremos una imagen movida.
Sí.
O sea, eso es lo que queremos hacer.
Esto no es lo que quieres hacer, pero es el resultado que tienes. Si yo funciono con esto, pues sale la imagen movida.
Vale.
Then, if I have 3 deltas and compute the third of 3, then I'm adding 3 images that are being shifted. And if I have 5, and if I put all the deltas very close to each other, then I have the same effect, but it's not as obvious as this one. Here it is very obvious. But here, it's not so obvious. But we know that the same is happening. So it is shifting by just a little bit, and then computing the average. So it is a little bit of a drag. So get blurred in the image. And this blurring can be seen, for instance, in very small details. So, for instance, here you see separation between two regions, and this separation is much more diffused in the blurred image. So, yeah, so this is strategy that I have. So let's say that we want to see if the delta convolved with the kernel still gives the kernel. So this will tell you have to shift your image up and so left and up, and multiply by 1. So multiply by 1 and shift left and up, and then shift up but multiply by 0. Shift up and right but multiply by 0. And the same for the other pixels. And now you take all the red images and you add all of them. This is the result. So it still keeps the delta. Okay, so I'm going to show you. I'd like to show you something that I have mentioned. Is this line one that is something like I don't see. I will look for it later. But there is one in which, as you said, if you convolve with something like this, see, if you convolve with something like this, you are having a blank image. So you did this on purpose because you have simulated, you have the forward pass. But you can do it also in the backward direction. So you are given this image. And then you said, okay, try to estimate what was the shape of the camera. When you take a picture and it's move, there is a convolution with some function. Estimate that function, and then you estimate this, and you can undo the movement. And it's a very nice application, but I cannot find now very quickly some nice images showing that. But yeah, this is interesting. You can go forward or you can go backwards. So once you don't know how to go forward, you can correct it. Okay, then yeah, this is too detailed about what is happening in the borders of the image. So when you are shifting your image to the locations of the kernel, the full convolution will be a little bit wider than the original image. These are also with signals. So you have a signal with one distance. diagonal derivation. So if you have a signal that goes exponent goes from 0 to n minus 1, so that n samples, and then your kernel has and your kernel has m minus 1, so total n signals, n samples. So the convolution of the two, x of n or with h of n, will mean n plus n minus 1 signals, samples. Yeah. So it is wider than the original. So for images, it's also small, but this is too detailed for what I do. So we will skip a few slides here. Yeah, here it is a nice illustration of the shift shift multiplier. So let's say that our image is this one. Let's say that this is our kernel. Now the coefficients will be colors. So you have to shift 2 pixels to the origin is here. So you have to shift 3 pixels to the left and multiply by blue. Okay, so now we have 2 pixels to the left and multiply by purple, by red, by yellow, and then 1 green, down, and then 2 down and multiply by blue. And then you add everything. And you keep the central region, or you give the final result with everything. So it is up to you, or up to the application to decide whether you are giving only the region where it is fully defined, because here in this region they are full of zeros. So either you only return the part that is fully defined, or you return the whole thing. Exactly. Again, to detail for this. Okay. So let's say that we have a couple of images like this, and we compute something. Yeah, we are blurring, so we are using this kernel. Okay, so we have these kernels and more blurring, even more blurring, a lot of blurring. And then at some point we lose some details inside them. See, the finer details here, they are so much blurred that you lose them when you do a lot of blurring. And again, this is the forward way, but if you know what the blurring is, you can go the backward way and try to recover the original way. And instead of convolving with blurring kernels, we can convolve with a different kind of kernel. So let's see, we can convolve with this kernel. So the kernel now kernel is like this. Minus 1, 0, 1. This is the origin, and sample everywhere. Okay, so what is this kernel? This kernel is delta r minus 1, 0. This is x, y. This is x, this is y. So this would be 0, 1 minus delta r minus 1, 0. this one corresponds to this. This one corresponds to this. So now, if I have an image, I of R control H, this would be, now I'm copying directly the result. So this would be I of R minus 0, 1 minus I of R minus 1, 0. And this is the same as of I have written here x, y. This is not x, y, this is y, x. This is y, x. So it doesn't matter as long as you are consistent. I have put 1 here because the second one is x. It doesn't matter if it is x, y, or y, x. And you have to be consistent. Okay, so this would be y x minus 1 minus I. Now, I was thinking right. 0 minus 1. This is 0. 0 minus 1. 0 and then 1 plus 1. So this is the equivalent. Let's make it 1 d again. So let's say that my kernel now, this is h, okay? This is n, this is plus 1, this is minus 1. And now you control with this. So y of n is x over with h. And this would be x of n plus 1 minus x n minus 1. And this is an approximation to the derivative. So this is an approximation. So let's say that we have a signal. So that we have a signal x of t. We have samples x over n. So we have samples. And I want to estimate what is the derivative at this point. So one approximation would be to take the nearby samples and compute the slope of that. So this derivative, would be the derivative. So the derivative of the point would be h goes to 0 or x of t plus h minus x of t minus h be the derivative. Now forget about limits. We forget about the limit, and we take samples. Okay, so what we are saying is an approximation y will be an approximation of the derivative will be x of, this is the next sample, x plus 1 minus x of n minus 1 divided by h. So h. And the interesting part here is this one, because the denominator is just a scalar, it's just a scaling. So you see, these kind of structures, they are approximation to derivatives. And then, if we look at our image, our signal before, we have the same structure. So this is the derivative in x. And then we have the derivative in y. So if we want to approximate the derivative in x, all we have to do is to convolve with this kernel. And then we have an approximation to the derivative in x. So yeah, so this is the same that I was saying, but now in a graphical way. So you can have I'm computing the derivative. This is C minus 1. I explained with C plus 1, C minus 1, but all of them have the same type of structure. So let's say that I convert with C minus 1, then you are running in this direction. So you have zeros, 1, zeros, and then 0 minus 0, so all the time is 0. When you reach the edge, you have 1 minus 0, so the result will be 1. And then you will have 1 minus 1, the result will be 0. At this point, you have 0 minus 1, so it will be minus 1, and then 0 again. So if you go in this direction, you have a couple of passes. One when you reach the edge, another one when you leave the edge. And let's say that instead of convolving with this, you convolve with this one. So now you will have, so this is 1 pixel minus the 1 on the left. This is 1 pixel minus the 1 on the right. So now you have the same kind of response, but now in the opposite direction. So when you enter the edge, you have the 1. When you leave the edge, you have minus 1. You have zeros everywhere else. And you can add the 2. So if this is an estimate of the derivative, and this is another estimate of the derivative, I have the 2, I have another estimate of the derivative. And by adding the 2, what you have is twice the central pixel minus the 1 on the left minus the 1 on the right. And from numerical methods, you know that all of these are approximations to the derivative. Okay, so now we have something. So computing the derivative is a way of detecting edges. And we can detect horizontal edges. So you convert with this one, minus 1 to minus 1. That was the one that we had here. Or you turn your kernel and then you detect vertical edges. Or you add the 2 kernels. Now we are detecting horizontal and vertical edges. And these are the expressions similar to the ones that I have been writing here. All the coefficients multiplying and shifting versions of the image. can detect edges in vertical, horizontal, both of them at the same time. And then we can apply them to these sample images. So for instance, let's say that we convolve with this kernel. So this kernel is vertical derivative. So let's look at the image again. So these are vertical, not vertical, horizontal lines, and then the vertical derivative is giving you edges that you find. These are the edges that I find. But when I compute the derivative in this direction I don't see any edge. So when I convolve with that, what I have is 0. And then where there is some small edge because of the change of intensity, I will have a little spike. I will have some response here, but then 0 again, and then 0 again. So I'm missing all the vertical edges. And the same happens with these squares. So these squares, most of them, so in this direction there is no edge. So in this direction, I don't find anything, and I only find the edges that I find when I'm traveling in this direction. So, and this is by computing derivatives in this direction, and then here we have the same effect. So you see the bottom and top sides of windows or the house, but you don't see the horizontal ones. So these are in this direction. I don't see that this wall doesn't have any change. So the wall is disappearing. And the same happens in the opposite direction. So now if I'm computing derivatives that are horizontal, now these are the lines that disappear. Now in this direction I don't see any derivative, only this one. And then the walls, the lateral walls of the house, I see, but the top and bottom of the windows I don't see. And then the two, now you see all the edges. You can compute diagonal derivatives. So, and then, for instance, this is very interesting. See, this was the original image. So let's look at this. So in this direction, the derivative is 0 all the time. So they disappear. These two squares disappear. Because in this direction, there is no derivative. There is no change. And now if you turn your kernel, now these two are the squares that disappear. You can compute derivatives in all directions. You can add the 2. You can add the 4. So horizontal, vertical, and the 2 diagonals. Then you will see all possible changes in all directions.
Y la de H plus D, esa no.
Esta.
La anterior.
La anterior. Esa.
Esta, sí.
Esa es horizontal y vertical.
A la vez.
A la vez. Bueno, añado los dos kernels, entonces los cambios en horizontal y en vertical. Pero como también lo puedo hacer en diagonal y puedo añadir todos los kernels que yo quiera, pues lo que estaría añadiendo es interesante eso, porque tú puedes hacer esto. Puedo tener una imagen y la convoluciono con un kernel que me va a dar los bordes verticales. Más un kernel que me va a dar los horizontales. Los horizontales. Más un kernel que me va a dar el diagonal. Nosotros me va a dar diagonal 2. Pero esto es lo mismo que calcular cada esto, sumarte, igual resultado, y sumarte todo lo demás. Vale. O sumo a nivel de kernel, o calculo cada uno visual o lo sumo todos.
Pero visualmente, o sea, por menos fáciles, pero si tengo datos, ¿sería posible verlo así?
Si tienes tantos,
O sea, si por ejemplo tuviese todos estos seguidos, como en el ejemplo.
sí, mira, aquí los hemos puesto todos. Simplemente pongo como cada kernel, mira, como cada kernel.
O sea, sí, entiendo, el vertical sí que lo veo y ahí puedes llevar, pues aquí hay un kernel que es horizontal,
Sí.
luego vertical, pero cuando están todos juntos.
Cuando están todos juntos no lo sabes, pero como
Vale.
ese kernel has podido después de descomponerlo,
Vale.
entonces esta dirección te calcula esta derivada en esta dirección.
O sea, de descompones.
Claro. O sea que convolucionar nos sirve para detectar cortes. Una forma de detectar cortes. ¿Alguna cosa más? No. Con esto ya terminamos. Bueno, vamos a ver.